All right, let's go ahead and get started. So today is one of the most fun lectures, for me at least. It's on more data parallel algorithms, but we're going to talk today about how you use things like scans and reductions and so on. So just to remind you, we're going to work today mostly in a completely idealized model of a data parallel machine, which is a machine that has an unlimited number of processors. And it has, we don't worry about the cost of control or the cost of communication. We do worry about the fact that sometimes processors will need to be turned off and things, but since processors themselves are free, as long as we're doing useful work, we'll just be worrying about the span of the algorithm. That is how many steps it takes in time to compute. And this will be useful for understanding the limits of parallelism. Let me skip this one. Okay, so I'm going to just start and go into a few examples here. And the first one is hopefully pretty simple. But please stop me with questions if you have at any point throughout, because I will be trying to walk through some of these examples. And if you get sort of left behind at a certain step, it'll be hard to probably catch up later. So in this first one, we're just going to try to compress a stream of values with where we have some values that we want to keep and some values that we want to throw out. And so we have an array of flags of ones and zeros. And so the ones will be the elements of the other array that we'll keep, and the zeros will be the ones we'll throw out. I think this is pretty straightforward. And so we've got our value array, and then the output is just to compress it into the set of the blue values that are in the values array. So 3, 4, 1, 3, 1, and keep them in order also. Okay, so it's just a couple steps. We're going to compute an exclusive add scan of the flags array, that first array up here. So that gives us, remember, an exclusive one says that the sum of is everything to your left. It's the sum of everything to your left in an exclusive as opposed to inclusive scan. So the first one is a 0 because there's nothing to the left. The second one is a 1 because there's just a 1 to the left. And the next one is also a 1 because everything to the left is a 1. There's one and a 0 that are being added together, and so on. And then we're going to take this array and we're going to do a scatter of this array into the result array. And we're only going to do that where the flag values are ones. So there are 5 ones in our flag array, and our index has 5 different unique values in it, so 0 through 4. And so each one of these will get a unique location to go into. So there's our original array, 3, 2, 4, 1, 5, 3. And the only things that are being written are the blue ones. And so, that the 3 is being written at, well, we go back and look at the index of that 0th position there, and it's a 0. So 3 goes into the 0th position. The 4 is in the position with a 1, so that goes into the first position, and so on. So any questions about that? Okay, we'll use this kind of idea in the next algorithm, which is a radix sort. So did you learn radix sort in 61B? I don't know whether people are doing it. So maybe you can raise your hand in the poll if you remember radix sort from 61B. So many people here. Okay, it looks like, oh, maybe some people have seen it. Okay, good, but maybe not. Okay, so you have seen it in 61B. Great, we've got a good. So hopefully this will be a little bit of review, but I will go through it in some detail to make sure that that we see. Let me just get rid of my participants list. Okay, great. So so what are we going to do? We're just going to radix sort this array, and I'm going to start by just reminding you of the serial algorithm. Hopefully this is a little bit of review, but it's important that you really understand this algorithm deeply before we try to parallelize it. And the reason we'll pick this algorithm is because for GPUs in particular, is because we want to have this data parallel style where basically everything, we've got lots and lots of fine-grained processors, All of them are going to be working at kind of one element at a time, and they're going to be, and we don't have any branches in the code. We'll have some masks and things, but not too many branches where we go have a bunch of, and so you can see how that would be different than something like merge sort or quick sort, where you really have, again, merge sort, the most natural way to write is with recursion, and that would that might be a nice thing to use on in OpenMP by using tasks in OpenMP, but maybe not a great fit for a data parallel model. Okay, so the idea with radix sort in general is that we sort one bit at a time. So radix sort is really nice if your keys have a limited range on them, so you know what the maximum value is and the minimum value. So we start with the leftmost. When we're doing our sorting, when we only sort one bit at a time, every time we sort, we're going to take all the zeros from that bit position and put them on the left, and all the ones, and we'll put them on the right. I guess my hands are going the opposite way, and then, but anyway, hopefully that gives you the idea. And we're going to use, when we do that sort, that one bit sort, which is just going to put the zeros on the left and the ones on the right, we're going to use what's called a stable sorting algorithm, which I think you also learned about in 61B. So a stable sorting algorithm is one that only reorders the things that it has to reorder in order to make the list sorted. It doesn't sort the other things. It'll leave the order of everything else unchanged. And that's very important to making radix sort work. And then we start with the least significant bit and we move up. And that may be a little bit counterintuitive, but the important thing is in the final answer, it's really important that you get, the biggest values over on the right and the smallest values on the left. And then the ordering within that kind of big set and within the small set will be set by the earlier sorting stages. And because we use stable sorting, that'll be preserved. Okay, so we're going to sort on the least significant bit. So think of the bits. In this case, we just have the value 0 through 7. So we just have 3 bits in all of our keys. And that will make it a small enough set that we can run an example here. And so the first thing we're going to do is to sort on the 0th bit, which is the rightmost bit, the least significant bit. So we're going to put all of the ones that end, all of the evens, which end in 0, before all the odds. So I've just marked the evens in blue and marked the odds in orange. And so this is what we want to do in radix sort. We're just going to, and notice that we're doing a stable sort. So we're keeping 4260 in order, and then we're keeping 7351 in order. And next we'll sort the entire array again. So it's not just sorting a piece of it or anything. We'll sort the entire array on the next bit, which is the bit 1. If you and so bit 1, we're going to take everything that's got a 1 in the sort of 2's position. So that is we put so 4, 2, 6, and 0 are all going to end up 4, 0, 5, and 1 end up on the left, and 2, 6, 7, and 3 end up on the right. Okay, so we now have some odd things on the left and some even things on the right. Then our next step is to sort, next step is to sort on the next bit, which is going to be, so this array, but now we're sorting on the bit 2, which is really basically all the large things versus the small things, everything that is greater than or equal to 4 versus everything less than, just because our total size of our numbers goes up only to 7. And so we put, oops, I think I flipped the colors here, but we put 1, 2, 0, 0, 1, 2, and 3 get sorted on the left, and 4, 5, 6, and 7 get sorted on the right. And notice that in the previous line, they were already correctly sorted within those 2 groups. So we just had to put the big things on the right and the small things on the left. Okay, any questions about radix sort? Hopefully that is review. Okay, so now we want a data parallel version. And all we're going to do in this data parallel algorithm here is really one step of that radix sort, which is just trying to sort on one bit, but stably sort on one bit. So we're going to preserve the ordering, and we're going to move, say, all the evens to the left and all of the odds to the right. And so here's our algorithm here in white, and all of these steps are really just going to do that one step, and then we're going to have a repeat loop across the bits. But we'll just walk through one execution of this. And what you should be looking at here is that each of the operations we're doing is a data parallel operation. That is, it's going to do something independently on every element of the array, or it's going to do something like a scan operation that we've already talked about last time, can be done in logarithmic time, log-n time in an unlimited number of processors. Okay, so the first thing is to compute a separate array called odd. So we're going to make up a whole bunch of temporary arrays in here. This is going to be written in sort of a functional style so that it makes it easier to see what's going on. And so we compute a new array called odds, and that is just basically looking at the last bit of everything in the input array, and it's setting it to 0 if it's an even and setting it to 1 if it's an odd. And now we can, by the way, think of this as it's also going to be a mask. We'll use it in both the even and the odd direction on the input array. So I've just colored the input array to match that mask array. Okay, then we do the opposite. So we can just in parallel do a complement of the odds array and get the evens array. And then we're going to compute something called the evens position, or evpos, which is the exclusive sum scan of the evens array. So that's just the array that was just before this. So it's exclusive. So the first element is always 0. And then the sum of the first element is 1. The sum of the first 2 is 1 again. And the sum of the first 3 is 2. Okay, and so on. I have stuck an extra element on the end of this because as we're computing this, we actually also want to know what is the sum of everything in the array. So we want the exclusive answers in each one of the elements, but we also want the 4 here, which is the sum of the scan. So as we're computing that, we can get that value out as well in a data parallel way. Okay, now we take that element, that 4, and broadcast it. So we can do that broadcast in log n time or log p time, but so we broadcast that out to a separate array, which is called the total evens array. We then compute, we then make an index array. And an index array is just an array of the numbers from 0 to n in order. So these are just constants. And so you could use something like kind of your thread ID. You can imagine at each one of these elements of the array in order to fill in a value, which is the value of that ID. And so that can be done in a data parallel way as well. Okay, now the next step is the hardest in terms of it being, we're computing the positions. So the evpos up here, and maybe we can go back and look at that array, the one with the extra element there sticking out. That's going to actually give you the position in the final array of the even elements. And the even elements, were the blue ones in the original array, so you could sort of look and see, or it's going to be the position that we want to put them into. Okay, and this one's going to compute the position of the odd elements. So that's the odd positions, and it is the total evens, so 4 plus the index that we just computed, so the number 1 through 7, 0 through 7, minus the evens position. So why is that? Because the evens position is going to give us the index of those evens, which are going to go at the bottom of the array, and the odds have to end up at the top of the array. So we have to have the total number of evens, which is 4. We've got to have that space for those. And then we're going to take that index 0 through 7 and then subtract off that even position that we had before. Okay, so now we compute essentially the merge of the even positions and odd positions. So this can be done, and maybe I said this here, this can be done with 2 masked assignment operations. So the first one masks takes the odd pos and masks it by the odds array at the top there, the second line. And the second assignment does an assignment of the even pos with the evens array into those positions. And so we get now this merged array of positions. And then we're going to do a scatter. So this arrow should have been pointing a line above. That was saying what I said, which is it's using 2 masked operations. Okay, now the scatter operation is going to scatter the original input array based on the position in the pos array. And it's going to do that with it's like putting the answer, the result, and then putting the pos array as the index into that. So what does that say? Well, the 0th index is that we're writing into is, if you look at the position array, that gets the 0th item, that goes into the 0th position. So that is a 4. And if you want to say, well, where does the 7 end up? The 7 ends up in the 4th position, because in the pos array, the second element here, right above the 7, is a 4. And so that ends up in the 7 in the 4th position in the output array. The 2, if you look above the 2 in the input array, right in the second to last line, it's a 1 right above it. Somebody showed me a little trick. No, I don't think that's working here. I had to get a pointer. And so the 2 ends up in the second position here in position 1, and the 6 ends up in position 2, and so on. And so what you can see in this output is that we've indeed sorted it in such a way that all the evens are on the left and all of the odds are on the right. And now, in order to actually do radix sort, we have to repeat this with each of the other bits, just as we did in the sequential algorithm. But now you've just seen how we execute the parallel algorithm using only data parallel operations. Any questions? Okay, and just to sort of point out that people really do use this on GPUs, these are some performance results from a paper by a Berkeley student and 2 NVIDIA employees, actually the head of research now, I believe, at NVIDIA, Michael Garland. So this was done in 2009, and this paper shows the implementation of a fast GPU optimized data parallel radix sort algorithm on the left, and a merge sort algorithm on the right, which is also optimized for the GPUs. It's important to look at the 2 axes here. So this is running time. And so the slowest point here, and these are different GPUs. So that's on the GTX 280 was 600. And on the merge sort, the slowest time there was, which is even a smaller number of keys. So the keys ends at 12 million, rather than over here, it goes up to about 17 million. And you can see that this, the merge sort time is over 1400 milliseconds. So that's the, and you can see the merge, even on the faster the GTS, for example, you get faster running time on the radix sort. Okay, let's see. So the next example I want to talk about, yes, these are old GPUs. That paper was from 2009. Okay, so the next example I want to look at is list ranking. And it seems like this may not take as long as I thought, but let's go through and talk about list ranking. So here we're looking at a linked list that is spread out over our parallel processor, our data parallel machine. So think of these as being a big distributed array, and the pointers point to the next element of the array, but the next element, sorry, of the linked list. So each array element has 2 things. It's got a value, and it's got a pointer to the next. And the pointer to the next would be a pointer to some other processor's element. And so although I've drawn this as a traditional linked list in order, it could be scrambled up all over the processors in any different way. And so the question in list ranking is to compute the distance of each node in this linked list from the end of the linked list. So you're trying to compute your rank. And so this seems like a fairly serial thing to do. You've got a linked list. How are you going to do anything other than walk through the linked list in order and count the number of elements, maybe go through it twice, and to say, I walk all the way through it and say, I think there are 10 elements in this list. So I'd put a 10 in the first one, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's the answer that I want to get out, is to replace the ones with those numbers. And you actually do want to do this sometimes in a linked list for various reasons. You can imagine there's other stuff in the linked list, but there's at least one of these elements that gives its rank. And so how do you compute this if you've got a linked list and you don't know how many elements are in it, or even what the rank of any individual element is? So there's just a little definition of the distance to the end. And you can see that we can just sort of walk through this, going through the next values and adding the current, adding a 1 to each, or adding the value to the next value that we got in the list. So as I said, this works even if the nodes are all spread out in funny ways across the processors. Okay, so what are we going to do? We're going to do this algorithm in steps. And so the first step is to look at your next and take the value that's there and add it to yourself. So value is initially equal to 1. That's what and then we set value equal to the next value plus, and add it to ourselves. So value gets set to 2 every place except on the second to the last element, where and I should say, by the way, we're going to destroy the list as we run this algorithm. You can imagine that you would have a set of temporary pointers, a copy of the next pointers, if you're going to run this on a real linked list, so that you wouldn't end up destroying your list as you go. But in this case, we will destroy it. So we set the next pointer to a null in the second to last element here, so that we can which is next.next. And we're also setting all of the pointers equal to their next pointer. So that's really key, is that the next pointers are not just pointing to the next element, they're pointing to 2 away. And if there isn't anything 2 away, then it's going to end up being null. So the next iteration, we do the same thing again. And in this case, we're getting 4s in all of these cases, because we're adding a 2 to whatever node it pointed to, which had another 2 in it. So those are all 4s, except you can see at the end of the array where some things that pointed to a 1 are going to get a 3, and the node that pointed to a 0 is going to end up with a 2. So you can sort of see how we're getting now the list ranking here at the end of the array. And the next iteration, we'll do the same thing again. This time we'll jump 8 away. And in jumping 8 away, a lot of them are going to end up with nulls at this point in the process. But they're also, as they do that addition, they're adding things like 3, 2, 1, 0 onto 4 and getting 7, 6, 5, 4, and so on. And so then we still have one more step left, and the last step, we are going to end up taking these last 2, I guess 3 pointers in here, and then adding 2, 1, and 0 to the 8, and ending up with 10, 9, and 8. So the key is that this is now a logarithmic algorithm. It is log in the number of list elements if we have an unbounded number of processors, and it's logarithmic in the number of processors even more generally. And so we're going to end up with, we can do this in a log n time on our idealized parallel machine. So any questions about that? Okay, next example, which is going to be a little bit silly because once again, we're computing Fibonacci in a completely inefficient way. But the observation here is going to be used for another example that comes up a lot in practice and is important for in actual hardware. And this example is computing Fibonacci. And so what the observation is, if you look at this Fibonacci formula, so f of n plus 1 is equal to f of n plus f of n minus 1, is we can make it a little linear algebra problem here by saying f of n plus 1 and f of n are equal to this little 2 by 2 matrix times f of n and f of n minus 1. So if you go and multiply this through, you end up getting this. You'll for f of n is going to be, well, the 1, 1 at the top times f of n, and n minus 1. So that gives you the sum you need for n plus 1, and f of n is then the bottom, which is just equal to f of n. Okay, so this little recurrence written out as a matrix multiply is going to be helpful in computing the Fibonacci in parallel in a data parallel way by actually adding up the numbers. And it's taking advantage of associativity of plus, which we're doing in all of these examples. We're taking advantage of associativity of either plus or one other operation like min and max and so on. And so we can compute all of the n Fibonacci's by taking this whole list of matrices, multiplying them all together, and doing a scan, that is, I'm using the word prefix, which is another synonym. It's a synonym for a scan. A parallel prefix is another word that we often use for that. So we'll do a scan, a multiply scan on this little array of matrices. And so each operation in that is a matrix multiply, which is also associative. And so when we multiply all these together, then we'll select the left element, left upper element, and that'll give us the answer of the Fibonacci number of this whole set of n numbers. So we've got n matrix multiplies we're doing. But we can do those multiplies in we can do a scan. And so we can do them in logarithmic time. So you can sort of see how maybe you can compute the product of all of these, a single product of these, by just computing each pair and so on, and then multiplying the pairs together and so on. Okay, so we're going to use a similar idea in a carry look ahead adder. And I think you learned about this in 61C, right? Tell me if you learned about carry look ahead adders in 61C. People aren't sure, maybe. So, okay, well, let's talk about what the hardware does inside of an integer adder. Okay, so now we've got a parallel machine way down inside of our arithmetic unit, and we're trying to figure out if we've got kind of long numbers, let's say a 64-bit integer. We're not going to worry about floating point here. A 64-bit integer, how do we add those up in such a way? Well, if you sort of did it in the usual, grade school arithmetic style, you start with the least significant bits and you add the least significant bits and then the next ones and so on, but you also have to carry, right? So you have to carry over if the product is greater than 1, then you have to carry the 2 over to the next column. And this is in binary arithmetic, but even in grade school arithmetic, you did that on if the result was greater than 10. Okay, so we're going to think of we're going to add A and B, and we're going to think of each of them as an array of bits. And I'm going to index them not from 0 up to n-1, but from n-1 down to 0, because that's the way we think of the least significant bits and so on, is the 0th bit is the rightmost one. And then the sum of A plus B is equal to, its own array, Sn up to S0, because we might have an extra bit that's carried into the Sn position. And we're going to use the what's called a carry bit array. We're going to have, and the trick is going to be to figure out how to compute this carry bit array. And the carry bit array is also indexed from n-1 down to actually past 0 down to -1. And we'll do that because it sort of makes the things line up a little bit better in terms of the indices. But it's still an array of n elements. I'm just going to write them as indexed from n-1 down to -1. Okay, so the formula for the carry array. So let me just go back. So adding together, the formula for the sum array should be pretty easy if we could get the carry array, right? Because it's just the bitwise sum of the A element, the B element, and then the carry. And that'll give us the bit answer that goes into that sum position. But here is writing it out a little bit more carefully. So we're going to use XORs and ANDs and so on inside of here. So logical operations also, but this is going to be a data parallel algorithm. So the last element of the carry array is going to be a 0, the rightmost carry bit. And we're filling it in like that just so we can make all the other formulas work. They can all look at their carry bit to the right. So the sum bit is the XOR of A and B at that bit position, right? So if they're both 1s, then it would be a 0. And if only one of them is a 1, it becomes a 1. And so on. And then we also XOR that with the carry bit at the position to the right. So the C-1 position, the I-1 position, sorry. So this is basically saying if there's either 1 or 3 1s, we get a 1. If there's 0 or 2 1s, we get a 0. And then how do we compute the carry bit at the ith position? Well, we take also this XOR of A and B at that position, but we do an AND then of the carry item. And then all of that, or we take if A and B, if that bit and AI and BI are both 1, then the carry bit has to be positive. And if the AI and B are, let's see, if the XOR of them is 0, but there's also, and there's a, sorry, and they're a 1, and there's also a 1 in the carry, then we end up with a 1. That says we sort of, the carry caused it to roll over to something greater than 1. Okay, so let's just look at a little example here, and I probably won't, I'm not sure if we'll walk through this in excruciating detail, but the example is written out in the slides, so you can go back and look at it later if you'd like. So here we've got the numbers, we're trying to add together the numbers 22 and 29. So I've written out 22 in its bit formation, bit format, and 29 in its bit format. And the carry bits then are this array that has an extra 1 on the left and an extra 1 at the right. And you have to sort of look at these formulas to see what happens. But for example, we're looking at the all of these values that are outlined here in order to compute the next carry bit that's in the and the next sum bits at the next positions. So we don't need the sum bits in order to compute, but to compute the output here, the 1, we're taking which is the 0th position. So S sub 0, we're taking an XOR of AI and AB, so that's a 1, and then an XOR of the carry, which is a 0, so we end up with a 1 in the sum bit. And similarly then, the carry bit, well, the last position was just automatically filled in by a 0 in the first statement. And the next one, I won't read through the formula, but you can go through the XORs and the ANDs, and that will give you a 0 in that position. And if you do this all the way through for the positions of C and S, you will get the right the answer that is shown here, which is indeed 51. Okay, so the challenge now is to compute the carry. So this one, the sum is something that can be easily computed in parallel. That's just an XOR of let's see, the A's and the B's. If we have this, if we have the carry array already computed, we can easily compute the sum in parallel. And so the question is how to compute the carry array, which has got this recurrence in it, right? It's got C of I is equal to some other stuff with a C of I minus 1 in it. So that's the only tricky part to compute. The S, once we have C computed, is going to be easy. And so we want to compute C in logarithmic time, log n n. Okay, so this is just from the previous slide. This is what the formula for the carry array looked like. It's C of I minus 1 is 0. And then for all the other elements, it's this somewhat complicated looking logical formula. And so we'll do this with a scan operation, a parallel prefix operation. And we'll do it by making up here some temporary arrays. One is called the propagate bit, and the other one is called the generate bit. And so this is also going to be an array of, both of them are array of bits from 0 up to n minus 1. And the propagate bit is the XOR of A and B, and the generate bit is the AND of A and B. So that's going to be used to compute the carry, right? The problem with the carry is that you don't really know whether it's going to be 1 or 0 unless you know what happened over on the right a little bit further. But this sort of says locally, if I just looked at A and B, it looks like with the XOR that I'm going to get a 1 in the answer, and then the generate bit is doing an AND of those two things as well. It's probably it's going to give you a number that's large. I say that between 0 and 1. Okay, so now we're going to write this out in a little bit of matrix notation, and that's why we did the Fibonacci example. We're going to the Fibonacci example is going to we're going to use the same idea of the matrix, not because we really care about computing Fibonacci in such an inefficient way, but because we're using the matrix example here. So there's a question in the chat. Didn't we say that each GPU thread is mapped to one vector element? In this example, each thread is accessing 2 C vector elements. So how does this work? Okay, it's a very good question. And in fact, as you learned, you would have to put these vectors in, if you were going to implement this on a GPU, which would be kind of a silly thing to do because we're talking about bits here, but if you're going to implement this on a GPU, at that level, you would have to put these arrays inside of shared memory so that they could access, so all of the threads could access within a thread group. And we have limited number of bits in our integers, so we can fit those inside of a thread group. And so within a thread group, they could access P of I minus one, or sorry, C of I minus one and C of I. And in our idealized machine model here, our data parallel machine, we're assuming that that kind of quote communication between thread 0 and thread 1, or thread 2 and thread 3 is free. We're assuming that that's the case. So it's not the case in actual hardware. We're going to need wires to connect those bits together and stuff. But fortunately, you're only going to need nearby things, and that's why this is actually going to be implementable in hardware. Okay, and let's see, I'm not sure I'm going to read through this, except to say that it very much looks like Fibonacci in that we're computing both C of I and then just sort of a 1 here. And we're taking this, we're taking this expression of the carry bit is equal to the propagate bit and the carry bit at the I minus first position, or the the generate bit at the ith position. And so that really comes from looking at this formula up here for CI and noticing that there's sub-expressions in here that are implemented by PI and GI. And then CI minus 1 is still there. Okay, so now we still have got this recurrence in here. We've got CI is equal to something that is a function of CI minus 1, but we can now write this little PI GI matrix as just think of that as a little matrix, kind of like our Fibonacci example. So we've got 3 non-zeros and 1 0 in that, and we can now do that matrix multiply in logarithmic time on our parallel machine. So what we're doing here is just computing the product of all of these matrices that all have the same shape. They're different elements of PI and GI, which were computed in a data parallel way, an easily data parallelizable computation of P and G. And then we take those and we compute a scan of this using this little 2 by 2 matrix multiply scan. And that's what it says. It's a 2 by 2 Boolean matrix multiply, which is also associative. And by the way, this is actually used in real computers down at not at the GPU level, but at the arithmetic level. And it even was implemented in the original Babbage machine in terms of this carry look ahead idea, a fast way to compute arithmetic. Obviously, things in this mechanical machine are very slow. You don't want to, be computing on 32 bits serially, so it does a parallel computation there. Next time, I'm going to talk about some examples that use segmented scan, and I will just, so I'll just mention here that the segmented scan is another primitive that I didn't really have a chance to talk about last time I think in any detail. We can implement what a segmented scan does, and I'll probably introduce this again next time when we use it in an example, but it's going to take in some array of values, an associative operator. So it's going to do a scan, just like, say, our sum scan, something like that. But it takes in segments. And so the segment says, only do the scan within that segment that starts with, say, a 1 in each of these cases. So the second array here has mostly zeros. And then the ones are saying where each new segment starts. So the first set of elements is a segment. The second, the orange group is a segment, the blue group is a segment, and so on. And you can see that other than the first group, which is automatically its own segment, everything else starts with a 1 in that second flag array. And so if we do a segmented sum scan on this input array 1 through, the numbers 1 through 8, segmented by this flag array here, then the results are, and this is an inclusive segment scan. We can also do an exclusive one, but this is then saying the first element is a 1, the second element is the sum of 1 and 2, the third element is just the sum of 3, and then 3 and 4, and 3, 4, and 5, and so on. So that's a segmented scan. And it hopefully should be obvious that on our ideal parallel machine, although I didn't show you an implementation last time of a segmented scan, we can certainly do a segmented scan in logarithmic and log n time on an unbounded number of processors. We just have to be careful as remember, you're implementing that scan, which we're going to be looking at in a lot more detail in homework. In the homework assignment, when you're implementing that scan, there's certain places where you would have to look at that mask array and then not propagate the values down, not add the extra values that are coming in, say, from the left. Okay, so a little bit about, I gave you one example of how one of these algorithms, the radix sort, got used on GPUs, and you'll be looking at implementing one of these data parallel algorithms, well, a scan in the homework. And but you might also wonder, there's other kinds of parallel processors, and one of the things that I had said earlier is that these data parallel algorithms can be a really elegant way of coming up with a way of executing parallel things on other kinds of machines. So they'll actually be useful also in the distributed memory clusters that we'll talk about in Unit 4. But here, even thinking about SMPs or those massively parallel machines, the main point here is that we don't have a processor for every element, or even, as in a GPU, where we really think of it as having a thread per element. It's not really a SIMD kind of architecture on an SMP, the kind that we talked about in programming in OpenMP. So what happens when you take these algorithms and you run them on a coarse grain parallel machine, like a shared memory multi-core processor, and kind of ignoring the SIMD units down the bottom of them? Well, if we're doing binary or unary operations on an SMP or an MPP, these are pretty straightforward to implement. So we can each processor is going to do the serial work of the things that are on that processor. Yes, we have to worry about communication if things are not aligned or whatever we need to do. But assuming that the arrays are aligned as they are in this picture, then the green processor can just add up the first four elements of A, B, and C and put them in A and B and put them into C. And the cost then of this binary or unary operations are just order n over p. So you get p speed up on them, which is the best you can do, right, on p actual processors. So now we're moving outside of our idealized model where number of processors are unbounded, and saying instead we have a fixed number of p processors, which are kind of hefty processors that can do a bunch of work themselves. In fact, they need to do a bunch of work themselves or they will not run very efficiently if each one is only computing one array element. And so in a shared memory multiprocessor, you could have some false sharing if the arrays are not well aligned. And so this goes back to things you worried about even back in the serial programming and things like that. In a distributed memory machine, it'll become much more obvious that if the arrays are not aligned, you have to actually communicate values between, say, the green set of the processor with the green elements and the processor with the orange elements and so on. But in any case, even on shared memory, you might worry about that a bit. Reductions in broadcast. So how do they work? In parallel, and scans can then be done in a similar sort of way. So there's a local sum that you do that has cost n over p. So that part of it is perfectly parallel, right? So each processor adds up, say, the 4 elements that it owns, and then it needs to do a reduction, and that has cost log p as opposed to log n. And so the real value actually of these data parallel algorithms on most real machines that we care about, I mean, even GPUs don't have an unbounded number of processors or free communication, but on things like a multi-core processor, you care about these kinds of algorithms that you can, that come to you because you're thinking about, well, what would I do if I had an unbounded number of processors and I want something that's order log n in the parallel scan time in that idealized machine, and that turns into something that's going to be an n over p plus just a log p factor, which is pretty small, right? But it's almost a p factor speed up here. And so you can do the same thing on a parallel prefix on a scan operation. And the way to look at this is the picture from last time, and I haven't drawn out all the details, but remember it was a recursive algorithm that does pairwise, say, additions, and then recursively does an inclusive scan on the half size vectors that you come out with, and then you use some combination of the elements that come out of that and the input elements to give you all of the answers in the output. And so this thing had height or log n in the original problem. In this case, it'll have height log p. And so there's a cost of doing the local scans in each one of the processors. And maybe the other part that's not completely obvious is you only need to take that one value and pass it to the right, for example, or pass something to the left. So each processor does its local sum, has to communicate a little bit sideways, and then you can do the because what's really happening in here is just a parallel prefix or a scan of the P elements that you get out of the processors. And so the serial time here is the N over P again, so perfect speed up plus another log P factor. And so a lot of times, when we think about these data parallel algorithms, we're thinking about the log n kind of complexity, which is the span, the theoretical time to run on an unlimited number of processors. But that is not the main reason that we use them. We really use them because of the fact that we get this, even on coarser grained parallel machines, sorry, you get nearly a linear speed up. So this is just adding up. Sorry. So let's say that we have 1,000,000 elements per processor, and we're trying to do a sum of those elements on each one of the processors. Well, we're going to have the K adds that are being done locally. So 1,000,000 of those adds, or 1,000,000 minus 1, I think technically. And then we have our log P steps, and then we've got our K adds that are being done. This is in our scan operation. So we're computing and storing the values of these elements. We keep all of the intermediate values of our K elements, so A0 up to AK minus 1. And then we do the parallel scan of these values that are the rightmost values that come out of each of the local scans, which were done serially. And that takes our log P steps. And then we take that back and add the local scan result to the result you got from the right. That'll give you your results are shifted over by whatever came in from the left. And so this is really, of course, what dominates this is the local adds that are being done on the left and the right in terms of the computational complexity. And even in practice, assuming P is a relatively small number, if P were 1,000,000, and by the way, there are machines that have that many cores on them, but if P were 1,000,000 and K was only 10 or something, you'd have a big problem in this middle piece. But in general, we're gonna run problems where the left and the right terms dominate. So this is just a list of some of the places that these scans get used in a bunch of cool parallel algorithms. One of the ones maybe that was most surprising more recently was some work done at Berkeley by a grad student, and Ross Bodek, who was here at the time in the faculty, looking at layout, page layout in a browser. So are you using a multi-core processor to do fast rendering of a website, and using one of these sort of scan-based algorithms in order to do that, because there are dependencies on where you're going to put things on a web page. You can see a whole bunch of linear algebra problems here. There's also there's a problem of parsing. And so if any of you have taken 164, you can actually use, this, the scan algorithm to do a parallel, to do a lexical analysis to find the tokens inside of a string, say in a computer program when you're trying to parse it and turn it into the kind of internal representation of that program. And let's see. Oh, the other thing, there's a question on Piazza about this, which is some of these examples. So the parsing example, which is in the kind of the slides, maybe the backup slides, I can unhide them, but I didn't go through it here. It's a pretty complicated to walk through, but I will unhide it and put it online, is from a paper by Danny Hillis and Guy Steele. And that's a really good reference if you want to look at the historical perspective of these data parallel algorithms. And that paper was written at a time when we were designing SIMD, large-scale SIMD parallel machines, when the parallel machines really were these massive numbers of little tiny processors. And so that's where those algorithms came from. Unfortunately, I think some of these other people have rediscovered algorithms for GPUs, but it's good to go back and look at I think that paper has a bunch of great examples, like the list doubling example in it and things like that. And then you can look at some of the GPU's papers, like the one I pointed to on sorting, which is a good reference for more recent implementation of these kinds of algorithms on GPUs. Okay, I should have flipped this slide though. So there's the reference. I knew I had it in here somewhere for the Danny Hillis and Guy Steele paper on data parallel algorithms. There's also a great YouTube video, I think Guy Steele does, that you can find by searching for his name. And Guy Blelick at Carnegie Mellon has a really nice language, a data parallel language called Nestle, which is nested data parallel, and has a paper from 2006, which is revisiting, it's an older language. And so some of these are kind of old things, but yeah, it's a great model to think about parallel algorithms. If you run into a problem that doesn't seem very likely to be parallelizable, then think about running it on a massively parallel SIMD machine and see if that helps with your algorithmic thinking. All right, any final questions? Great, thanks very much. We'll see you next time.